All right, so a couple of logistical questions before we start. Piazza is set up, so you should be able to ask questions about Piazza. I know that some of you still have questions about joining the course and, getting out of the wait list. I think that it shouldn't be a problem because, again, the expectation is that a few people will drop. So, last year there were lots of people on the wait list and people are, kind of feeling a little bit, am I going to get in this course and not get in this course? At the end of the day, everybody got in the course because a whole bunch of people dropped the course. So, just be patient. There's also an online section. And for people who are in the online section, also for this section, you're more than welcome to just look at the lectures online. You should be able to log in through Blackboard or Canvas, and these lectures are recorded. People who are taking online section, if there is a space, you're more than welcome to come and listen to the, the lectures. There aren't going to be any difference between the two sections. So homeworks, midterms, final projects is going to be the same for everyone taking section A or B. The other thing that I want to point out is that a few of you are auditing the class. So for people who are auditing the class, your only requirement is going to be to do the final project. Okay? So for folks who are auditing the class, because marking assignments is a little bit tough. So far we have 4 TAs, it's going to be 5 TAs. We try to get the 6th one. So that should happen pretty soon. Also, TAs will have office hours. That was posted on Piazza, okay? So starting this week, TAs will have office hours. If you have any questions, I think right now we have 2 or 3 TAs actually holding office hours. So it's like 3 hours of office hours every week. So take advantage of this in particular. Next Monday, the hope is that by next Monday, I'm going to give out the first assignment. And in the first assignment, there's going to be a bunch of questions plus the programming question. And I'll tell you a little bit more about it next Monday. You'll have 2 weeks to do the assignment. There are going to be 3 assignments. Few people asked about midterm, the dates for the midterm. The plan for the midterm is to make it during the first, or maybe during the 2nd week of October. Okay? So I haven't set up the date yet. There are a few constraints, but planning to have a midterm either on October 10th or 7th or 8th and such. I'll get back to you exactly what date it should be. Okay? I'll just have to figure out where we're going to write the midterm because it's supposed to be an in-class midterm and there aren't big enough auditoriums that can fit everyone. So that's my challenge. In the worst case, the midterm is going to happen here, and we just have to deal with it, I guess. Sorry about that, but if right now, when I look at the overall people who are registered on Piazza, of course, people are choosing and coming from the wait list and dropping. But right now, the number of people who are taking the class is about 300. So we'll have to figure things out as we go along. Okay, so bear with me. Any other questions, logistical questions? I know a lot of you are emailing me personally asking things about how do I get off the wait list and so forth, but just because there are so many emails, unfortunately, I can't respond to each individual one. So if there are any sort of common questions, please ask those questions on Piazza. TAs will try to answer. Are there any other questions before we get into the lecture? Okay, so the other thing that I also wanted to highlight is that for those of you who are planning to take the course, you should start thinking about projects, right? That's one thing that you should keep in your mind as we go through the course. It's a little bit too early right now, but nonetheless, keep thinking about it, okay? Okay, so last time, so today's lecture, let me just give you a little bit of outline where we're going to go with the class. today is going to be the last day where we're going to be doing a little bit of review of distributions and exponential family models. This isn't going to be important for us when we're going to start looking at graphical models and Boltzmann machines. A lot of that material will come up. So this might be a background for many of you. Starting on Monday, we're going to start looking at neural networks. So we're going to have lectures on neural networks, backpropagation, dropout, batch normalization. So there's going to be a little bit more recent techniques for training these models. And then the following week, we're going to start looking at convolutional neural networks, the idea behind those. After we're done with these basic modules, we're going to start jump into generative models, where we're going to look at Markov random fields, Boltzmann machines, and something more advanced type of models. Okay. Okay. So Bernoulli distribution. Remember last time we quickly looked at the Bernoulli distribution. This is going to be your friend throughout the rest of the class, right? So make sure that you are very much familiar with this class of distributions. Anytime we're doing binary classification, anytime we're going to be working with Boltzmann machines, variational autoencoders, a lot of the times we're going to be working with Bernoulli distributions. That's kind of like the first thing you should know about is the Gaussian. The second one is Bernoulli. There's two things you should know about. Remember, you have a binary random variable, which is 0, 1. The probability that x takes value 1 is going to be determined by parameter mu, right? So the probability that x takes value 1, given the parameter mu, is going to be given by mu. And mu is constrained to be between 0 and 1. The probability distribution, this is known as a Bernoulli distribution, is going to be written this way, right? And you can see that if x takes value 1, then the probability that x takes value 1 is going to be just given by mu. If x takes value 0, the probability that it's going to be taking value 0 is going to be 1 minus mu, right? Very simple, very intuitive. You can compute the expectation. This is an interesting one. The expected value of x is going to be 1, right? When we remember how we compute expectations, right, it's x times the probability. If x equals 1 times the probability that x equals 1 plus x given 0 times the probability that x given 0, which gives you mu. Okay? And you can also compute the variance. Parameter estimation. How do you do parameter estimation? Suppose we observe the data set D. We can construct a likelihood function, which is going to be a function of mu, which is going to have this form. Now again, remember here we're going to be making ID assumption. So we can write down as a product of individual probabilities, right? Which is going to take this form. Or equivalently, you can maximize the log likelihood function. So the log of the probability, the data, given the parameter mu, is going to have this particular form, right? In fact, this particular form will keep seeing a lot of it. For those of you who've ever played with neural networks and trained classification models, that should remind you of being something that's known as a cross-entropy error function. We'll come back to that when we start looking at neural nets, but this is roughly where it comes from. So here it's this is your observation, and this is your parameter that you're trying to estimate. Okay? So the likelihood here depends on the n observations on xn only through the sum, right? So if I push this sum, if I push this particular sum inside here, then you can basically see that if I'm trying to estimate this parameter mu, it really depends on just the sum of xn's, right? And again, as I mentioned in the last class, this is known as sufficient statistics, right? And we will come back to the notion of sufficient statistics when we're going to look at exponential family models, when we're going to look at Boltzmann machines, graphical models. This is going to be a key concept for us, right? Something that we'll come back later to is something that's known as expected sufficient statistics, which is going to be important for doing maximum likelihood estimation for a lot of these models. Okay, so that's an important concept, right? And it's also in your mind, you should think about sufficient statistics as a way of, you don't really need to carry the entire data set. Right? The only thing you need to know is for estimating the parameter here, like if you think of it as being a coin flip, you don't need to remember individual coin flips. To estimate this parameter, you just need to know how many heads, you flipped. Out of let's say 100 flips, 50 were heads, right? And so now we have the likelihood function. How do we estimate parameters? Well, we can do maximum likelihood estimation. How do we do maximum likelihood estimation? Well, we can take the derivative of the log likelihood with respect to parameters. And that's going to be the common theme through the rest of the course, right? We write down the likelihood function. We differentiate it with respect to parameters that we're trying to estimate. In this case, it turns out there's a closed form solution. You take the derivative, you set it to 0, and you find the maximum likelihood estimation. Right? So in this case, m here is the number of heads, for example. Right? Number of times x takes value 1. Very simple. But nonetheless, this is how we would do maximum likelihood estimation. Binomial distribution. Last class, we quickly looked at the binomial distribution as well. So the probability of observing m heads given n coin flips, n parameter mu is given by this expression. So binomial distribution is kind of like an extension of Bernoulli, right? It really is telling you what's the probability that you observe m heads given n flips, right? And again, the mean and the variance can be the expected value. Oh, something is wrong. No, my PowerPoint crashed again. Sorry about that. I don't know, it's getting worse and worse. Maybe Microsoft is trying to tell me to start using Microsoft Surface instead of Mac. Let's hope that we won't see a lot of crashes again, but okay. Right, so you can compute the mean and you can compute the variance. For those of you who haven't done these calculations, I would encourage you to just go through the math, right? It's a little bit of linear algebra, but if you haven't done this, like for example, computing expectation of the binomial distribution, it's just go through a little bit of math. And this is the histogram. For example, binomial distribution is a function of m for n flips when mu equals 0.25, right? So think of it as a biased coin. The probability of heads is 0.25. And now you're saying, what's the probability that you observe 0 heads? What's the probability that you're going to observe 1 head or 2 heads or 3 heads and so forth, right? So if the probability of flipping a biased coin, the probability of heads is 0.25, then obviously you can estimate what's the probability you flip this coin and 7 times you're going to have heads. It's going to be pretty small, right? So the mean is kind of sits around here. So that's the distribution. Beta distribution, again, we quickly went over this distribution last time, but just as a reminder, beta distribution, you can define the distribution of a parameter mu, right? So it can be used as a prior over the parameter mu of the Bernoulli distribution. This is something that's, again, a distribution defined over the interval 0, 1. Right? It's heavily used in Bayesian models, and maybe in one of the classes in this class, we're going to look at the Bayesian neural nets. It's heavily used in Bayesian models because it can be specified as a prior over the Bernoulli distribution, right? Over the parameter of the Bernoulli distribution. And again, just quickly, this is what these distributions look like, different parameters, right? So it's kind of interesting. If I set A and B to 1, it specifies uniform distribution over 0, 1, right? If I specify 0.1, 0.1, has masses around 0, 1, right? And so you can kind of, depending on the parameters of this distribution, you can have fairly different distributions. Multinomial variables. This is something that I think that if you haven't had much experience with multinomial random variables, again, I would encourage you to look at that distribution, because anytime we're going to be looking at softmax or we're going to look at the multi-way classification models, this is going to be your friend. So for the multinomial distributions, think of it as a random variable that can take on one of k possible mutually exclusive states. So we're going to be using so-called one of k encoding scheme, right? So let's say if a random variable takes on 6 states, and for a particular observation we observe the third state, right? So x3 equals to 1, then x will be represented this way, right? So you have 6 states, and you're basically saying that it takes, state 3, right? So there are 6 possible outcomes. It takes the third outcome. So this is known as a one of k encoding scheme. And we're going to see later why this is a useful encoding scheme, as opposed to just representing as state 1, state 2, state 3, state 4, 5, or 6. Okay? The important thing is that if we denote the probability of xk equals to 1 by the parameter mu k, then the distribution over x is going to be defined this way. Okay? So think of it as, we have mu k's from 1 to 6. Each mu k specifies what's the probability that the random variable will take, state k, right? Obviously, they have to be positive. They have to sum up to 1, right? So I have 6 states. Mu k specifies the probability of me being in each particular state. Then I can write down the likelihood function, the probability of particular x, this way, right? Using one of k encoding scheme. Obviously, if x takes value 3, then if you look at this product, only mu sub 3 will survive. So the probability of this x, 0, 0, 1, 0, 0, 0, is going to be mu sub 3. Okay? And, they can be viewed as a generalization of Bernoulli distribution to more than 2 outcomes, right? Because now you have k outcomes. And it's easy to see that that distribution is normalized. First of all, if you sum over all states, you're going to be summing over mu sub k's, all of them. You're going to have 1. And the expected value of x, given your parameter, is going to be given by a vector of mu. Which is, again, you can see as a generalization of Bernoulli distribution. It only has 2 states, 0, 1. Maximum likelihood estimation. How do you do maximum likelihood estimation? Imagine you have a data set, of rolls of dice, x1 to xn. You can construct a likelihood function, and likelihood function will take this form. Let's look at this form a little bit more precisely. It's the product over all the data points, right? Because again, we're assuming IID assumption. This represents a particular probability of a particular x, right? Here, x and k basically represents the state, whether the variable takes, what's the kth state for the nth random variable, right? So we have n of them. And effectively what we can do is we can just basically push this product inside here and just represent it this way. Where mu sub k is the number of times a particular number of times these random variables take state k. Right? So this is what the definition of mu sub k is. And again, you see that the likelihood function depends on the n data points only through these quantities, right? If you abstract it away, maybe through the equations, let's say I have a dice, maybe biased dice, that has 6 states. I roll it 1,000 times. And I tell you, estimate me probability that the dice has, that if I roll it, it's, what's the probability that I'll see 1? What's the probability that I'll see 2? What's the probability that I'll see 3? How do you estimate it? Forget about equations. What would you do?
The number of times you roll it each time.
Yep.
Divided by all of them.
Yeah, exactly. You roll 1,000 times. You see how many of those times you've seen the dice being rolled as 1, or as 2, or as 3. And you count how many times you see each particular instance divided by the total number. That's exactly what the maximum likelihood solution will tell you, right? This is the maximum likelihood solution. So it's very intuitive. And this is just represents the number of observations that particular state k took place, right? And again, these are the sufficient statistics for this distribution, right? Number of times you're observing the value of each state. The interesting thing now is that, you can find the maximum likelihood solution, but you have to take into account the constraint that these mu sub k's have to sum up to 1. So you have to be, if you're not familiar with Lagrange multipliers, I think that in the Bishop's book and the deep learning book, there's a section on Lagrange multipliers that you should look at. It's basically, you have to form a Lagrangian, which is the likelihood plus the constraint that these things have to sum up to 1. And it turns out that if you solve for the maximum likelihood solution, then naturally it comes down to being mu k, which is the number of times you observe a particular state, divided by the total number of random variables, or total number of rolls, right? So the maximum likelihood solution is exactly what you would expect. Okay? Any questions? Which is the fraction of observations for which xk takes value 1. Okay? Multinomial distribution. This is just for your knowledge. Multinomial distribution, it's kind of like when we looked at the Bernoulli distribution as generalization, this is kind of a multinomial generalization of where you're basically saying that, well, you want to construct a joint distribution over these quantities. So it's basically telling you what's the distribution of seeing mu1, mu2, m1, m2 up to mk, right? So if I roll my dice 1,000 times and I ask you, what's the probability that I get to see 200 times, 200 ones, 200 twos, 300 threes, and so forth, right? So you can specify that distribution. So it's sort of a generalization of the previous distribution. There is a mean, there is a variance, and it's basically, and then you have a normalization coefficient here. It's looking at the number of ways of partitioning n objects into k groups. And sum of mk should be equal to n. Okay? Multinomial distributions will use that, but not as frequently. So we're going to be looking at, if I go back, we're primarily going to be looking at multinomial variables, right? Kind of just as opposed to multinomial distributions, even though that concept will come up later. There's also a class of other types of distributions called Dirichlet distribution. This is something that you should be familiar with. Maybe we'll touch upon that distribution later in the class again when we're going to be looking at Bayesian neural nets. And it really is a fascinating class of distributions. So let's say you have a distribution over mu k, subject to the constraints that these mu k's should be positive and they should sum up to 1. So this is really distributions defined in a simplex, right? And Dirichlet distribution is defined that way. If I look at the equation, probably it doesn't really tell you much, except for you have these parameters, alpha 1 up to alpha k, right? It's a simplex in k-dimensional space. And these are parameters of the distribution. And then this is a gamma function here, which is just a normalizing. And it's you can think of it as a distribution which is defined or confined to be a simplex as a consequence of these constraints, right? They have to be positive and they have to sum up to 1. So any point here will satisfy these constraints, right? And Dirichlet distributions, like if you look at machine learning literature, if you're interested in Bayesian statistics, there's a whole class of beautiful algorithms called, Dirichlet processes, where you're essentially defining distributions over, over these mu k's, which themselves, parameters of a multinomial distribution, right? So you can introduce the notion of priors and so forth, right? We're not going to talk much about that particular framework in this class, but nonetheless, you should be familiar with these distributions. And it's kind of interesting. Depending on different choices of the parameters, you can have very different shapes of the distribution, right? When alpha k's are basically equal to 1, you have uniform distribution over the simplex. When alpha k's are fairly small, you have basically strong priors on the corners of the distribution. So you're basically saying your mu sub k should be 1, 0, 0 or 0, 1, 0, right? It's almost like saying if I roll the dice, I have a very biased dice. I'm always going to be rolling 1, or I'm always going to be rolling 6. And then if you set your alphas to be pretty high, then they sort of concentrated in the center, which basically means that every outcome is, has the same probability, or almost the same probability, right? Which is if you roll a fair dice, then that would happen. Okay, and now, again, this is the class of distribution Gaussians, and for many of you, I think, and again, you should be very familiar, but just to mention that we're going to be working with the Gaussian distributions. You should, for the univariate case and its multivariate extension, you should memorize this equation. That's one of the things you just should know. So this is a Gaussian distribution. You have mean, you have variance. The Gaussian distribution satisfies that it's positive and it integrates to 1. Right? So if you integrate this Gaussian distribution from -infinity to infinity, you have 1. Multivariate Gaussian distribution. We're going to be making use of multivariate Gaussian distributions through the rest of the course. When we're going to look at variational autoencoders or extensions of graphical models, you'll see this equation a lot. So again, my recommendation will be just memorize this equation, right? Just know what the multivariate Gaussian is. One of those things that you just should know, kind of like a multiplication table. The multivariate Gaussian distribution is governed by 2 parameters, mu and sigma. You have a d-dimensional mean vector, and sigma is a d by d covariance matrix. And this is the determinant of sigma. And one thing to note, and we're going to be making use of that, is that the variance, the covariance matrix, is symmetric positive definite matrix. Okay? Central limit theorem, just a little bit of detour. Sometimes we're going to be making use of that, but the distribution of the sum of n ID random variables becomes increasingly Gaussian. So let's look, if you look at n variables, each of which has uniform distribution over interval 0, 1. If I look at the average, as the number increases, as n becomes larger and larger, it will look increasingly Gaussian. Okay? In the rest of the course, we're going to come back to this point again. It's kind of fascinating. For those of you who are not, probably many of you are familiar with central limit theorem, right? It's the kind of thing you'll learn in like a second year or third year statistics course. Moments of the Gaussian distribution. The expectation of the Gaussian distribution is given by mu, right? So let's look at this expression. How do we compute expectations? Well, the expectations is you take, this is your probability distribution, you multiply it by x, and you integrate, right? One thing we can do here is we can use this expression, right? So I can pull up I can do change of variables. In this case, I did change of variables by basically saying x minus mu is going to be the new z, right? And now x minus z, which gets converted to this. The question is, we know that the expected value of x is mu, right? It's the mean. Why? From this expression. What happens to this guy? Yes?
It's an odd function, so it goes to 0.
Exactly. So this is an odd function. It basically means that when I'm integrating from -infinity to infinity, if I integrate by parts, if I go from -infinity to 0 and from 0 to infinity, this term will be 0. Right? Because it's kind of like symmetric around 0. Right? So whatever integration here and whatever you do here is just going to be 0. By symmetry. So expected value equals to 0. The second order moments of the Gaussian distribution are given by this expression. It's mu transpose plus sigma. And it's a very good exercise to go through that definition through that algebra if you haven't done this. It kind of tests your knowledge of your linear algebra and a little bit of algebra manipulation. But you can actually go through the definitions and derive that. So the covariance is given by, this is the expression, and that's the covariance matrix. Right? And the expected value of x is given by mu. And so obviously the parameter matrix sigma here governs the covariance x under the Gaussian distribution, so that's why it's called the covariance matrix. Now if you look at the Gaussian distribution, these contours are basically showing you contours of constant probability density. Generally, if the covariance matrix is in general form, it can be shaped in any way. Whenever you have diagonal covariance matrix, it's going to be axis aligned, right? So this is an axis aligned. If your covariance matrix is diagonal, if it's spherical, which is proportional to identity, think of it as your covariance matrix is alpha times identity, where alpha is some parameter. That is going to be spherical, right? Like this. It's going to be proportional to the identity. So sometimes when we do estimation or we fit the covariance matrix, in many cases, particularly when you're dealing with large-scale data sets, people either prefer to choose your covariance matrix to be diagonal or spherical, right? Because there's fewer parameters to estimate. Later on, when we look at some classes of models, like when we look at variational autoencoders or when we look at graphical models, we are going to be looking at covariance matrices that have low-rank decomposition, right? That will have low-rank structure. So again, it saves us on the number of parameters that we need to estimate. Yes?
In figure A, the covariance matrix contours, if the major diagonal is an acute angle with respect to the x-axis or anything, is that a positive correlation?
Yeah, so this would show a positive correlation, right? But in general, if you look at the covariance matrix in general form, it can be any shaped covariance matrix, right? Now, generally, we'll come back to this. Couple of things that you should be familiar with. Let's say we have a partition X into two disjoint sets, XA and XB. Okay, so we have X, we have XA and XB, and we have partitions of mean and covariances. And in many cases, later on, it's going to be important for us to work with inverse of the covariance matrix. Sometimes it's called precision matrix, right? So think of your precision matrix as being the inverse of the covariance matrix. And one thing to note is that this element is not given by the inverse of this element, right? It's just, hopefully you know that. Nonetheless, in many cases, when we're going to be looking at conditional models, we're going to be looking at conditional distributions. The beautiful thing about Gaussian distribution, that's why a lot of machine learning deals with Gaussian distributions, is that you have these explicit manipulations that you can do. So for example, you can compute what's the probability of XA given XB, right? The probability of XA given XB is given by, the covariance is actually given by, take the precision of AA and just look at its inverse, right? So that's sometimes, it's easy to do. If you already have precision matrix, you just invert the corresponding elements of the precision matrix. The mean is given by this expression or this expression, right? So it can be in terms of the precision or it can be in terms of the covariances. Now, these equations don't really tell you much, except for one thing to keep in mind. Interestingly, the covariance matrix, right, of the conditional Gaussian does not depend on XB. Right? It doesn't really depend on the state of X, what you're conditioning on, right? It also has this interesting property, which you can think of it as the reduction of uncertainty, right? So you have some covariance minus something positive. So conditioning on something always reduces your uncertainty about random variable XA. And the other thing about the mean, the conditional mean, is that it's a linear function of XB. Okay? So those are the two properties that we have from conditional Gaussians. And when we're going to look at, again, linear dynamical systems in this class and extensions, these equations will pop up. I'm not expecting you to memorize these equations, and I'm not going to ask you on the midterm, like, compute this thing, because you can, look at, but you should just be familiar with the expressions here. It turns out that the marginal distribution of a Gaussian is also Gaussian, right? So the conditional is Gaussian and the marginal is Gaussian. And it's actually pretty easy to compute. If you look at the marginal, what's the probability of XA? You have to integrate out X sub B, and it turns out that this is just given by, the marginal distribution, you just take this, this, and this element, which is kind of neat. Later on, when we look at normalization or marginalization, it's very easy to deal with Gaussians, right? It's almost no computation. This just shows you the differences. Let's say this is a joint distribution of XA and XB. And if I say, let's say XB equals 0.7, right? If I look at the conditional probability, what's the distribution of XA given XB equals 0.7? Then you're really looking at this slice, right? And that's what this distribution would look like. That's what conditional distribution would look like. If I look at the marginal distribution, what's the probability of XA? It really is projection of this distribution onto this plane, right? And that's going to be your distribution, right? So you can see the difference between the marginal and the conditional. So conditional, obviously, note, as I mentioned before, your uncertainty shrinks. It's always going to be shrinking. If you condition on something, it will shrink. Of course, if you condition on something on like XB, and XB is independent of XA, then, there's going to be, the variance is not going to shrink. But generally, if some correlation, it will shrink. Maximum likelihood estimation. You can construct the log likelihood function this way. You can say the log probability of X. This is just taking the log of the Gaussian, the multivariate Gaussian. And again, this comes as sufficient statistics for this Gaussian model. You're just basically looking at the sum of xn's and sum of the second moments, right? And that's generally the case that if you want to try to estimate, the Gaussian distribution, all you need to do is you need to look at the sums of xn's and just look at the variance, right? That's all you need. Or in this case, look at the second order moments. The other thing I would want to point out for the rest of the course is that sometimes when you're working on a particular problem and you have this particular expression somewhere in your equation, it's probably with high probability you can probably derive a Gaussian distribution out of it. So roughly speaking, whenever you're working with something, you have something squared, it has some relationship to Gaussian, right? Remember, I think that a couple of classes ago we looked at the sum of the errors, sum of the squared errors, right? And whenever you have something squared, you can probably redefine it back to being a Gaussian distribution, right? So how do you find the maximum likelihood? To find the maximum likelihood, you set, again, the derivative of the log likelihood with respect to 0. So if you set the derivative with respect to vector mu, you're going to have this expression. And you can solve it to get maximum likelihood estimation, which is just the average, right? Same thing happens for the estimate of the covariance. Now, you have to use matrix algebra here to figure out how to differentiate with respect to the matrix. I believe that you have part of your homework, not part of your homework, but part of your reading material are the sections that actually go through this derivation. Right? So you might want to go through that derivation just to see how it's done. But in general, if you take derivative with respect to log likelihood function with respect to sigma, you're going to end up with this expression, which is, again, just looking at the covariance, right? Which is what you would expect. So evaluating the expectations of the maximum likelihood estimates under the true distribution, you can actually obtain these equations, right? So let's say, how do I obtain the first equation? Well, this is my expression here. I can take an expectation with respect to the Gaussian distribution. And if I can take the expectation with respect to the Gaussian distribution, the sum of the expectations, so expectation of the sum is the sum of expectations. So I can push that through and get the mean. Okay? If I do the same thing for the variance, for the covariance, I'm going to get this expression. Okay? So when we look at the estimation of the mean, sometimes we would call it to be unbiased estimate. And when we look at this expression, this would be called a biased estimate. Right? It's biased because like expected value of maximum likelihood estimation doesn't equal to the covariance. Right? And so we can construct the unbiased estimate by defining this variance. Right? If n is pretty large, it probably will not matter that much. But if n is small, in some statistical procedures, you're going to be using that as an estimate. Question for you: why do you think if I look at this expression here, why do you think that this is a biased estimator? Have you guys taken any stats classes before? What's the intuition? Why is it a biased estimator? Yeah?
Because the mu ML is non-mu.
Exactly. If you look at this thing here, it's a maximum likelihood estimation. If we knew the true mu, then this would be an unbiased estimator. But because we're already using 1 degree of freedom in one-dimensional case to fit these parameters, that's why your estimation becomes biased. Right? Later on, we'll come back to this question, particularly when we're going to be looking at sampling methods, like importance sampling. And we'll see in some cases, we will see these biased estimators pretty much because of the same problem. Okay, another class of distributions you should be familiar with is a student t distribution. It has this particular form, not quite, revealing, but to think about this distribution, it's a Gaussian distribution where you have mean, you have precision tau, and then you have a gamma, you can think of it as a prior over precision tau, and then you're integrating it over the tau. And lambda, eta, and nu is given by these parameters. So this is a student t distribution. Okay. You can think of it as an infinite mixture of Gaussians. Right? If I were to approximate this integral with discrete choices, then I have like a whole bunch of taus. And for each tau, I have some prior distribution over the tau. And sometimes this is called precision parameters. These are degrees of freedom. But why is this distribution important? This distribution is important because for different choices of the parameters, you can get a distribution that has heavy tails. So for example, when nu here goes to infinity, you recall a Gaussian distribution. But when nu equals 1, you have Cauchy distribution. And Cauchy distribution is a commonly used distribution, particularly when you want to have heavy tails in your distribution. Why heavy tails? In many cases, these kinds of distributions can be more robust to outliers, right? And this is quite important. Sometimes people are, for computational reasons, people, instead of using Cauchy distributions or something more complex, people do use student t distributions, or they use mixture of two Gaussians, one with small variance, the other one with large variance. Kind of mimic this effect that once in a while, if you get an observation over here, then it still will have some probability under the heavy tail distribution, which under the Gaussian, it will have almost 0 probability, which would be really bad for your estimation. Right? So here's an example. Here's your distribution. You're fitting a Gaussian distribution. And let's say you have these 3 outliers. Your student t distribution doesn't really change that much. But your Gaussian distribution is shifting its probability mass because it has to account for these observations. Right? So its mean and its variance is going to be much more spread out. So when you think about building robust models that are, important for the outliers, student t is your choice. And actually, a few papers, if you Google some of the papers on training neural nets, sometimes people do use student t distributions. And the properties of this distribution is you have mean, you have covariance, and you have mode of x, and so forth. Right? So this is just for your own for your own information. The other thing that we will talk about briefly through this course in the context of neural networks also is this notion of mixture. How many of you work with mixture of Gaussians? Raise your hands. A few. Okay, not a lot. This is your, a really good friend for modeling the data. This is kind of like old data sets, but very well-known data set, right? So you can fit a Gaussian into this model, but it's going to be very bad. Why is this bad? Because it's basically saying the most probable configuration is over here, which is not the case. If you fit a mixture of two Gaussians, you have, you're modeling the data much better, right? And then there are like a few papers of people arguing, are there two Gaussians or are there three Gaussians? How many of you think that there are three clusters here? No? How many of you think, okay, maybe how many of you think there's two clusters here? Most of you, okay. Well, that's not the case for the researchers because, some people think there's actually a cluster over here, right? So sometimes when you model this data, it's very hard to say exactly how many components you want to have. And there's a whole class of different algorithms that, try to figure out what's the right number of components you should have in your data. Mixture of Gaussians. The idea behind mixture is that you can combine simple models into complex ones by defining superposition of k Gaussian densities this way. So this is a Gaussian, this is a Gaussian, this is a Gaussian. If you combine three of them, you can model fairly complex distributions, right? And this is one of the techniques that, in some of your homeworks, hopefully you'll compare to. These are very effective techniques. If you look at speech recognition, mixture of Gaussians, mixture of 1,000 Gaussians, it's very hard to beat. This is known as a mixture component. These are known as the mixing coefficients. They have to sum up to 1. They have to be positive. And each Gaussian has its own mean and its own covariance. So it can be fairly flexible in terms of what you're modeling. And in general, there is a class of mixture models where you can combine linear combinations of other distributions. So there's some interesting work that basically says that each thing here is actually going to be a neural network. So you can combine a whole bunch of neural nets, and this would be called something that's known as a mixture of experts. Each expert could be a neural net, and you have a combination of them. And you have these pi k's, which can tell you when you trust one network over another network. Right? So that's something we will briefly cover in the class. But I just wanted to show you that this is, if we have three Gaussians, if I actually look at the marginal probability distribution, this is what I'm modeling. And this is what these three mixture of Gaussians can model. Right? You can see it's a fairly sophisticated distribution. You can't model this distribution using student t distribution or a Gaussian distribution or anything sort of like simple distribution. Right? So you can actually model fairly complex distributions using mixture of Gaussians. Right? And this is the contours of the marginal distribution, the surface plot of the distribution. Maximum likelihood estimation. How do we do maximum likelihood estimation in this model? Maybe just quickly. Given a data set, we can determine the model parameters, the means and the covariances of each one. The problem is that generally there is no closed form solution, right? So for those of you who worked with a Gaussian, there is a whole class of algorithms called expectation maximization algorithms. We're not going to cover those in this class. But you can use iterative numeric optimization methods. And generally, when you look at the problem of log of a sum, there's going to be generally no closed form solution. In fact, in many cases, we're going to be looking at the log of the sum of exponentially many terms. And if you look at machine learning, I'd say 60% of the problems are trying to solve log of the sum of exponential number of terms. So anything that has to do with graphical models, marginalization, and so forth, it really just comes down to how do you solve log of the sum, which is kind of sad if you think about machine learning, but generally that's what everybody's trying to solve. So for the last part of the course, I just want to give you introduction to exponential family models, and this will conclude kind of the review part that we need for this course, okay? So make sure that you have a good understanding of all of these models, because I'm not going to come back to these definitions. So exponential family of distributions over X can be defined in a more general form, right? So exponential family is defined as a set of distributions of this form, okay? So eta is the vector of natural parameters. U of X is the vector of sufficient statistics. So it's an inner product of natural parameters and sufficient statistics. The function g here, which is a function of eta, natural parameters, can be interpreted as a normalizing constant, right? It's the coefficient that ensures that the distribution is normalized. Okay? And h of x could be any other function of your data. Generally, h of x is going to be 1. So in this case, if I take this this expression here, right? If I integrate this, it has to sum up, it has to integrate to 1, right? That's just the definition of the probability distribution. Okay? So 3 things we need. We need natural parameters that we're going to be estimating. We need sufficient statistics, and we need the normalizing constant. Sometimes this will be called partition function. It comes to us from statistical physics. For those of you who, taking any stats courses, you would know that partition function, estimation of partition function is like one of the biggest problems in statistics. A lot of work using variational methods, Markov chain, Monte Carlo methods are trying to estimate this quantity so that we can get access to these distributions. Okay, so why is this important to us? Well, it's important to us because this particular class of models, exponential family models, generalizes pretty much all the distributions we've looked at so far. I can write Bernoulli distribution, beta distribution, I can write Gaussian distribution, all of these gamma distribution, exponential distributions, I can all write them down as a member within exponential family models, right? Why is it important to us? Well, it's important that later in the class, we're going to look at Boltzmann machines. And these are models, we can say, well, let's assume our random variables are Bernoulli, right? And we derive, learning rules and so forth for that particular model. But if we can generalize and derive the learning rules for the members within exponential family, then I can just basically generalize Boltzmann machines to other kinds of distributions, right? I can generalize them to be Gaussians, to be Poisson, to be exponentials, and so forth, right? There was actually a nice paper about 10 years ago that basically showed how to generalize Boltzmann machines to members within exponential family models, which kind of like opened up a whole new class of models. So that's why it's important for us to know about exponential family models. But let's look at some of these examples very quickly. The Bernoulli distribution is a member of exponential family, right? That's the definition of the Bernoulli distribution. But I can express it in this way, and I can actually write it in this way. Okay? There's a little bit of math, but I can move things around. So compared to the general form of exponential family, the natural parameter is given by the log of mu over 1 minus mu. Right? Remember, mu is the probability of 1. 1 minus mu is probability of 0. And in fact, this parameterization sometimes makes more sense because you can think of it as a log odds ratio. Right? It's the log of, what is it, probability of 1 versus probability of 0. And these are known as the odds. In statistics communities, I think that people prefer to use this parameterization because it's more natural. Machine learning communities, people tend to prefer this because sometimes it's easy to deal with it for maximum likelihood estimation. And mu here is given by the sigmoid function. So the relationship between this parameterization and natural parameterization is just given by the sigmoid nonlinearity. Okay? But I can write it down in this form. Right? And this is logistic sigmoid. So if I look at this, I can write down the Bernoulli distribution in this form. Right? Where u of x is 1 h of x, sorry, u of x is x. So this is sufficient statistics. H of x is 1, and then this is my partition function, normalizing constant. Okay, very simple. Multinomial distribution. Remember, we've looked at the multinomial distribution this way. Same thing happens. X is given by x, and this is my natural parameterization. So I can write it down this way, right, where I can say my natural parameter is just log of mu's, other parameterization. But the parameters eta k's are not independent, since the corresponding mu k's have to satisfy this expression, right? They have to sum up to 1. So we have to do a lot of work to, to actually, I have to do some work to actually, let me just shut this down, sorry. I have to do some work to reduce this parameterization, right? Because obviously, my mu k's have to sum up to 1. There aren't really m parameters. There's really m minus 1 parameters, right, that I have to specify. If I specify m minus 1 parameters, then I can get the m fifth parameter, because they have to sum up to 1. But in many cases, it'll be convenient for us to remove this constraint. And define distribution over m parameters. Sorry, that's a typo. It should be distribution over m parameters instead of m minus 1 parameters. So generally, when we're going to be working with multinomial distributions, we're kind of going to be ignoring this constraint. And we're going to be specifying m parameters as opposed to m minus 1 parameters, natural parameters. We'll come back to that point a little bit later. But if you want to have this constraint, then you can set my mu sub m is going to be given by 1 minus the sum of the previous mu sub k's. And this will lead to this expression and the definition of mu sub k. And this is known as a softmax function. And in this case, mu sub k's will satisfy this constraint. This is known as a softmax function. And it also reduces this constraint, right? That's, you're basically not forcing mu sub n as an independent parameter. If you know these parameters, that's the definition of the last parameter. So you can basically, the relationship between mu sub k's and the natural parameterization is given by the softmax. In the Bernoulli case, it was given by logistic. Here is given by the softmax. So we will make these connections back and forth when we, going to be looking at classification models and such. And so in multinomial case, again, this is just the definition. For multinomial case, we can have this parameterization. This is the expression that can exactly fit it into this form, right? There's a little bit of math to keep up, and I might be going a little bit too fast, but this is something that you could look at yourself, because it's just simple algebra here. There's nothing specifically hard. Gaussian distribution. Gaussian distribution can also be written as a member of exponential family. This is a case of just a univariate Gaussian. And in this case, my eta here is going to be two-dimensional, right? The mean, the natural parameterization for the mean is going to be mean divided by variance. And natural parameterization for the variance is going to be 1 minus half of the variance. My vector of sufficient statistics is going to be x and x squared, right? Something that we've seen before. And then I can have hx, and this is my normalizing constant. Yes?
How do you choose the way to separate the three vectors of 2 pi goes to the
So 2 pi goes to this thing, right? Because this doesn't depend on eta, or it doesn't depend on, it's just a constant. Constants would typically go into the h factor. But it's not that important. I think what's important is this quantity here. This quantity here is important because that's a normalizing constant. And for the Gaussian distribution, we can compute it exactly. This is important because you see you have x and you have x squared, right? So whenever you have x and x squared, that turns out to be your sufficient statistics. There's no other way to factor it. Factoring it is also kind of difficult generally, but for a lot of existing distributions, we already know how to factor it. Here I'm just trying to show you that If I try to do maximum likelihood learning for this parameterization, then you can basically unroll it and apply it to any other distribution within the exponential family. There are members of distributions that are not exponential within exponential family models. Like, for example, mixture of Gaussians. Mixture of Gaussians cannot be represented in this form, right? Student T distribution cannot be represented in this form. So there are some distributions that are not members of exponential family, but a whole class of models that you're probably familiar with, like gamma, Poisson, Gaussian, exponential, Bernoulli, multinomials, they're all members of this class of models. So how do we do maximum likelihood estimation? Well, remember for the exponential family model, that's the definition. From the definition of the normalizing constant, I have this expression, right? If I integrate this whole thing, it has to be equal to 1. Okay? Now, I can differentiate with respect to natural parameters, right? Because these are parameters of my model. What do I have? Well, I have the gradient of this quantity, right, times this, and I'm in differentiating by parts, plus my normalizing constant, and then if I differentiate eta here, I'm going to have this term coming up, right? X is going to stay, u of x comes out. Okay? Now, you have to be careful when you put transposes and such. So you have to like match the dimensions. Kind of like the way you do it in your code is that put the matrix, dimensions don't match, flip it. If they match, it's good enough, right? So, but generally you have to be careful with transposes. Now, notice what this is. What is this? This is 1 over g, right? This is 1 over normalizing constant from this definition. You see that? Plus this quantity. What is this here? This is just the expectation of sufficient statistics, right? It's expected value of u of x. That's the definition. Okay? So now something interesting happens, and including this thing here, right? This is just the expected sufficient statistics. So now, if I take the negative gradient of the log of the normalizing function, I get expected sufficient statistics, right? How do we get here? It's a very useful trick to remember, because when I take the gradient of the log, what's the gradient of the log? The gradient of the log is 1 over, right? It's 1 over g times the gradient of g, which is exactly what this is. And when I pull it on the other side of the equation, I have the negative, right? So now you basically say that the gradient of the log of the normalizing constant gives you expected sufficient statistics, right? And this particular equation actually gives you what the maximum likelihood solution should be. Take the gradient of your parameters, set it equal to expected sufficient statistics. Solve for it, you get the answer. Sometimes this normalizing constant, sometimes we'll know, people call it partition function. We can think of it as a moment generation. It's a moment generating function. It turns out that the covariance of your sufficient statistics can also be expressed in terms of the second derivative of g. And similarly for the higher moments. So that's why this normalizing constant, this partition function within exponential family models is actually a very important quantity, right? When we're going to be looking at, graphical models, Markov random fields, Boltzmann machines, this equation will come into place. When we're going to be saying that, well, effectively the gradients, how do we estimate the gradients of the log of the partition function? The gradients of the log of the partition function gives us the expected sufficient statistics that we will need to do maximum likelihood learning or do maximum likelihood estimation. In the case of simple models like Gaussian and Bernoulli, this can be computed exactly, right? But if you want to derive, let's say, maximum likelihood learning rule for Bernoulli, you just use this parameterization for Bernoulli, take the gradient, set it to expected sufficient statistics, and then you get the solution, right? That's a stable and so forth. Any questions? Yeah. Oh, sorry. Yeah.
In general, when we're training a deep model, we might assume one particular form of the exponential distribution, say our outputs are Gaussian or that our outputs are from a Bernoulli distribution. If we wanted to be more general and train it with the exponential family distribution, is the only problem estimating a partition function there? Or like, why can't we be, why do we assume a specific form to it instead of just trying to be more?
No, you can be more general. I believe you can be more general, particularly when you try to solve the problem of y given x, like trying to predict some target y given x. In many cases, exponential family models, they're sort of more general. In many cases, if you assume some distribution for y, if you say it's a real value distribution, then you have to assume maybe that's a Gaussian. If you say that it has, Poisson-like distribution, like it's a distribution defined on like 1, 2, 0, 1, 2, 3, 4, like discrete set of spaces, then you want to use Poisson. But in general, you can define, learning rules and everything for the general class, and then kind of go down and say, if I'm working with this problem, I'm going to assume this distribution. If I'm working with this problem, I'm going to assume this distribution. For other types of models like Markov random fields in general, the big problem there, because these are generative models, you're trying to define distribution of a more complex space, partition function becomes the problem. So generally, this will be our bottleneck. How do we evaluate this thing? Because in many cases, we will not be able, if U of x is high dimensional, and it has, specific discrete structures that we're going to be looking at, then in generally, we will not know how to compute this expectation. We will not know how to compute the gradients of the log of the partition function. And so this is where a lot of more advanced techniques like sampling techniques, variational inference techniques, if you're familiar with beta approximation, it's kind of coming from mean field approximation. These are all statistical physics techniques. It's techniques coming from statistical physics that essentially trying to, estimate these quantities or estimate these quantities or estimate log of the partition function or its derivatives. But that is generally, most of the models we're going to be looking at are going to be members within exponential family. But in many cases, we won't be able to estimate these quantities exactly, because this can only be estimated exactly for very simple distributions. Right? Okay, so maximum likelihood for exponential family models. Now let's look at just the last thing very quickly. We can construct the log likelihood function, which is a function of the natural parameters. Right? So we can construct this expression here. If I get the set of x1 up to xn, these are my data points. Remember, that's the definition of the exponential family model. And so now, if you differentiate, you get this expression. Right? So the maximum likelihood solution here is going to be finding the natural parameters, the gradient of the log of the partition function of normalizing constant is going to be equal to the average sufficient statistics. So sometimes this is known. Remember, what is this thing? Actually, the gradient of the log of the partition function is the expected sufficient statistics defined by the model, right? If we go back here, this is what the thing is. And, oh, sorry. And if we're trying to estimate, this is the sufficient statistics driven by the data. Right? So later on, again, when we're going to look at generative models, we'll start seeing that the maximum likelihood solution is really given by, matching expected sufficient statistics driven by the model to the expected sufficient statistics driven by the data. That will become the core learning rule for a lot of different models. You just try to match the two sufficient statistics, right? And if you match them, then you have the maximum likelihood solution. And so now, if you want to do maximum likelihood learning for a bunch of Bernoullis or Gaussians or Poissons or whatever those distributions are, you just basically write in this form, write tests in this form, and that's the solution. You can just plug it in, take the derivative, set it, and that's the solution. Okay? Okay, so let's stop here. So on Monday, we're going to start looking at the neural net lecture, and hopefully assignment 1 should be out on Monday.